Good morning, ladies and gentlemen. It's a great pleasure to welcome you here. My name is Neese, and I will tell you a little bit about theoretical X-ray spectroscopy with ORCA. And before I do that, I want to give a big hand to Dr. Dimitrios Manganas. He has been working with me for more than 10 years, and he has done absolutely fantastic work. He did all of the hard work of implementing the methods that I will bring to your attention, and he has done beautiful applications. So practically everything I'm showing you is what Dimitrios has done with his group, and I'm very thankful for that, and I'm sure you will enjoy his talk too. So before we start to go into the nitty-gritty, let's ask ourselves, why should you care for quantum chemical X-ray spectroscopy? And I must say that I have learned practically all I know about it from my wife and collaborator in science, Serena De Beer. She's a well-known figure in the field, of course. And we have been working closely together, and much of what we have been doing is inspired by the needs and wishes that Serena has, and it's an absolute pleasure to work with her and her group. So why would you want to do quantum chemical X-ray spectroscopy? You will want to do that when you want a predictive tool that allows you to go directly from atomic coordinates to X-ray spectra without any parameters, without any fitting. And that difference between fitting and predicting, that is something very important that I think will come up quite a number of times during the talk. You will want to have a tool to allow for the assignment of experimental spectra. They can become very complicated, and to disentangle it, quantum chemistry can be of great help. And it's not only here in X-ray spectroscopy, we have seen that everywhere, and that's particularly also in high-resolution magnetic resonance, where quantum chemistry is an absolutely indispensable tool in order to aid and supplement the experiment. Quantum chemistry is also a tool to establish structure-spectra relationships. So when you ask yourself what in the structure is important for what spectral features, then of course you can ask quantum chemistry on model calculations. You can change the structure and can see how the calculated spectra react. So it's an incredibly powerful tool in order to give you insight into what structural details the observed spectra are sensitive to. It can be a tool to identify unknown species on the basis of the calculated spectra. So if you have measured something and you're not sure what it is, and sometimes a calculation can greatly help you to distinguish between the possible structural candidates, and that's a very, very useful tool, especially in catalysis. Quantum chemistry can be a tool to predict spectra before doing the experiment, and in some cases even it can help to debug the experiment or even help the experimentalist to design the experiment. That's actually a use that I didn't have quite on the radar, but Serena was very strongly insistent on that. And in fact, I learned over the years that her group, very often before they go to the beamline, they run some calculations to help themselves understand what they could expect, and more often than not, these calculations have been helpful in finding mistakes in the experiment that were ironed out. That is not saying that quantum chemistry is a perfect tool that is always super accurate, but it very, very often is good enough in order to sharpen your intuition and help you to sort out what's reasonable and what's not reasonable. And I want to emphasize that these are different goals compared to what one wants to achieve as a parameterized model, like the multiplet model. These things are complementary to each other. They're not in competition to each other. And that is also why Dimitrios will tell you later what he has developed lately, which is a quantum chemistry assistant multiplet model, where you can use the quantum chemistry to predict the parameters of the multiplet model. And then you have a standalone multiplet program that you can run these models through. You can change parameters if you want. So, and within fraction of seconds, of course, you can generate thousands of spectra. Whereas with quantum chemistry, of course, it's a much, much more elaborate calculation. Now, let's ask ourselves, when will these tools be useful? So one, and that I think is a strong condition, is that the tools have to be usable by non-experts, and they have to be non-experts with a high degree of confidence. It is pretty much like driving a car. Like, most of us are not very well versed in the technology of the car. Some of you may be, I'm certainly not, but yet we know how to drive a car with confidence. And you can use quantum chemistry in just pretty much exactly the same way. If you know what you're doing and you know what to look at in order to find out when it goes wrong. And that is necessary. Then. So it's pretty black box, but it's not 100.0% black box. In order to be useful, the calculations time have to be short enough for users not to lose patience. And I understand that you would want to have your answers basically immediately. That does not happen with quantum chemistry, but of course, if you would have to wait a month for your calculated spectrum, you wouldn't be interested. And I totally get that. So somehow, in the development, we have to strike a balance between the achievable accuracy and the computational effort, and that has always been a guiding light in whatever we have done in our development. Well, and then, of course, is the accuracy. The accuracy of the predictions need to be adequate enough for the tool to make any sense, right? If you calculate spectra that have the wrong number of peaks and they're all in the wrong place and they all have the wrong intensities, then these calculations are useless and they're not helping you. One thing that I, over the years, found not so important, actually, is to nail the absolute transition energy. Whatever errors we're making here are typically highly systematic, but what we really want is relative transition energies, and they should be reasonable. A lot of theoretical X-ray spectroscopy is strongly focused on getting the absolute transition energy to high accuracy. I personally don't. And once you have settled on a method and a basis set, your shift is absolutely systematic, and if you have determined it, for a few reference compounds that you know, you can apply that shift with confidence and get very, very good predictions. But the relative transition energies, they should be reasonable, and I'd say it's best if they're not, the errors are not exceeding a few tenths of an electron volt. And maybe half an electron volt may be acceptable, and unfortunately that's the type of error we frequently have, but it shouldn't be much larger than that before the tool starts to be too inaccurate to be usable. And then, and that's a pet peeve of mine, the number of features should be correct. And it's surprising how many calculations are done. It don't even predict the right number of transitions. And that is something that I find absolutely critical. And I will come back to that a little bit later in the talk. And of course, the intensity distribution in these peaks should be at least qualitatively correct, right? Then, so we're not doing absolute cross-sections, but the relative intensity should be qualitatively correct in order to allow for assignments that are reasonable and or even accurate. That is a fairly stringent list of requirements, but I hope to convince you that present-day quantum chemistry came a long way in being able to meet these goals. Not always perfectly, but in many cases, it's quite useful, and that is what I bring to your attention. So the tool that you will be using today is the ORCA project. The ORCA project is a big quantum chemistry project, and it's a very general purpose quantum chemistry tool. By now it has about 30,000 users, very quickly growing, and it's free for academics. You can download it from our website. And X-ray spectroscopy is only one thing you can do with it, but you can basically do almost everything that computational chemists want to do is implemented in ORCA. And today we will see what capabilities it has in theoretical X-ray spectroscopy. There is a very active user community. If you register in our forum, which you need to do in order to download the program, you will find many, many discussions there and many answers to technical questions. The community is very friendly and very helpful, and I recommend that you do that. Now, ORCA has been designed with the idea to be a universal theoretical spectrometer, and indeed we can calculate a lot of spectroscopic properties. So you see that X-ray absorption and LBS are just two of them, but there's also Mössbauer, there's all kinds of optical spectroscopy, vibrational spectroscopy, and the big focus has always been magnetic spectroscopy. So even if you have other experimental data that you're interested in, chances you can calculate these spectra with ORCA are relatively high. Now, turning to the theoretical X-ray spectroscopy with ORCA. So here is kind of an availability chart that shows you what methods can be used for what spectroscopic properties. And I've decided that I won't go into the theory of any of these methods here, because that would give a boundlessly long talk that would also be very technical and probably not very interesting to listen to. And here are the various spectroscopic properties, starting with KH X-ray absorption spectroscopy, L and MH X-ray absorption spectroscopy, X-ray emission spectroscopy, both mainlines and radiance to core features, and then more complicated spectroscopies like RIXS and XMCD, and finally also NRVS. And the first tool that comes to mind is TDDFT. Of course, DFT in general is a very useful tool. It's computationally highly efficient, but it has limitations. It does well for KHXAS, it does very well for X-ray emission spectroscopy, it does well for nerves, but I would not recommend to try to use TDDFT or DFT-based methods for L or M edges unless you have D0 systems or RIXS or XMCD. The tool that we have developed in Mülheim that is unique to ORCA is called the ROSIS approach, and ROSIS can calculate all of these spectra except nerves that is only available with DFT. And then there are other ab initio wave function based methods. These are all in the so-called multi-reference regime, and the simplest of that is RACI. RACI can calculate all of these spectra. It is a limited accuracy tool that, however, is qualitatively correct, and so it's a very, very useful starting point in order to play around, also since these calculations are not computationally expensive. More expensive, but also more accurate, is an FPD2 approach, which is a form of second-order multi-reference perturbation theory, and it has most of these spectra except XES, and then if you go to very high accuracy, that would be multi-reference CI or even the multi-reference couple cluster approach as implemented in the MRGON implementation in ORCA. Again, everything except XES spectroscopy. So what should you use? And of course, you have 1,000 options here. And what is what I recommend? And here's the recommended methods for different types of spectroscopy. So I would definitely recommend DFT to do KHXAS and XES and also nerves. These are nice applications of DFT. They typically work rather well, and they're very easy to use and computationally efficient. Then ROSIS, of course, can be used for any of these spectra also, and I think that is a mistake here. It can also be used for the X-ray emission. And it's definitely a better choice for LH, XAS, RIXS, and XMCD, as I will show you a little later in the talk. RACI can be very useful for XES spectroscopy, especially for calculating main lines where DFT totally fails. So DFT is only working for the valence to core region. And FPD2 is great for calculating LHs. It's a bit more expensive than ROSIS, so if you want higher accuracy and you can afford it, then FPD2 is a great choice. Also for RIXS and also for XMCD, same comments. It's a step up from ROSIS, but also it's a step up in terms of computational resources. And if you have tons of computational resources and a lot of patients, then you can also calculate LHs or RIXS spectra, also XMCD, sorry, that's another omission here, that's a mistake in the table, from MRCI and MRUN calculations. So in terms of like cost versus accuracy, the lowest cost definitely is DFT, and you can apply it to systems with maybe about 500 atoms. And of course, you can also apply it to extended systems like solids and surfaces, and I believe that Anneke will tell you later today how to apply ORCA in the framework of solids and surfaces and extended systems. But DFT is definitely the highest efficiency tool here. And the next in terms of the efficiency is ROSIS, and ROSIS quite typically is a step up in terms of accuracy. And we have developed a method that is very, very useful that we call PNO ROSIS. And PNO ROSIS is a way to make ROSIS calculations cheaper. So with that, you can also reach the region of about 500 atoms that you can apply it to, whereas normal ROSIS probably is between 100 and 200 atoms, will get computationally very cumbersome. But PNO ROSIS is a very efficient tool that is highly recommended. Then there is RACI. RACI probably can be used for about 100 atoms or so. We haven't quite done that, but I don't really see why one shouldn't. It's definitely doable. Then FBD2 is probably best applied to systems with less than 100 atoms. If you twist my arm, then I can probably do 100 or 150 atoms, but these calculations start to become quite expensive. And MRCI and MRUM are crazy, and you're definitely in the realm smaller than 10 atoms, and so that is mostly done when you want to do kind of pilot studies, or you care about very small systems, model systems that you are studying to figure something out in principle. So that basically is our truth table to orient you, and now we will start to dig into the science a bit. And I will start by talking briefly about one of my pet peeves, and that is what is it that we're really trying to approximate? And what we're seeing, of course, what any spectrometer sees are energy eigenstates, and so energy eigenstates of the Hamiltonian. I'm not talking about time-resolved spectroscopy here, obviously, so it's just like the regular static or time-independent approach that we're following here. And the molecule through the eyes of a physicist is relatively simple. It consists of positively charged nuclei that are practically at rest, or for the most part at rest, and negatively charged electrons, and they just have electrostatic interactions. And that is the content of the so-called Born-Oppenheimer Hamiltonian, nuclei at rest, electrons movable. And the Born-Oppenheimer-Schrödinger equation then is a many-particle equation, right? Because it contains these n sets of electron variables, and it contains a collective set of nuclear variables, nuclear position variables. And so since these are fixed, you solve, you treat these as parameters, so to say, and solve the electronic Schrödinger equation at fixed nuclear position. And that is an absolutely daunting task. And so we can't even do it exactly for 2 electrons, save the dozens or hundreds that are in our actual systems. But in principle, what we're trying to approximate here is, of course, the solutions of the many-particle Schrödinger equations, right? So it's a many-particle Hamiltonian, and it has many-particle eigenstates. And I'm making that strong contrast to the one-particle pictures that you have in DFT or Hartree-Fock theory. That is what can be observed. It's the many-particle eigenstates, nothing else. Yeah? And of course, you have to supplement that Born-Oppenheimer Hamiltonian for X-ray spectroscopy with terms coming from relativity. And the most important one in terms of X-ray spectroscopy is certainly the spin-orbit coupling, which is another 2-electron phenomenon. Most of the time, the spin-orbit coupling operator is approximated as 1-electron operator, which for the most part works okay. But there are also scalar relativistic effects that are to be considered. There are effects of the electron-electron spin-spin coupling. But I'd say by and large, the most important effects are the Born-Oppenheimer Hamiltonian, then those describing external electric and magnetic fields, like the Zeeman effect, and the spin-orbit coupling. These are the most prominently featured terms in the Hamiltonian, and we are faced with trying to approximate the many-particle Schrödinger equation. And let me make this clear. The difference between states and orbitals, what I just talked about is states. And in quantum chemistry, you never call an orbital a state. An orbital is a 1-electron function, and it's a million ways you can generate orbitals in Hartree-Fock or DFT or any flavor of DFT. There are many, many, many different ways, classes here, to generate orbitals, and they're quite typically optimized for a given approximate state, right? So orbitals arise in the so-called independent particle wave function when the many-particle wave function is approximated by an anti-symmetrized product of 1-particle wave functions, which are the orbitals. And quite typically, these orbitals, they come with orbital energies that would be the so-called canonical orbitals. And since we normally optimize the ground state, these orbital energies are associated with the ground state. Now you have occupied orbitals, you have unoccupied orbitals. And so you have the occupied orbitals in physics language are called particles, and the unoccupied ones are called holes, and it's all fine and reasonable. But what one shouldn't mistake, I think, or what one shouldn't do is to confuse the spectrum of one particle energies with the many particle spectrum. So the one particle spectrum in general has nothing to do with the many particle spectrum. It has completely different structure, and it is quite misleading. Also, the spectrum of particle-hole energy differences is not the same as the many particle spectrum. Yeah? There are some favorable cases where the spectrum of orbital energy differences has some resemblance of the many particle spectrum, but in general they have absolutely nothing in common. That's why a term like the density of unoccupied states doesn't exist in quantum chemistry. In quantum chemistry, a state is a many particle state, and an orbital is an orbital. An orbital can be used in order to approximate, like an ensemble of orbitals can be used to approximate a many particle state. But in general, these orbitals, they're not observable, and they're to some extent also arbitrary. And so it's very important in my mind to make this distinction. And I want to make that less abstract by showing you an example. So in KH absorption spectroscopy, you have transitions that are good transitions, so to say, where the one electron excitation or the particle hole spectrum is reflecting the many particle spectrum, and that is when you make a transition from W-occupied core orbital into a singly occupied valence orbital. Here, the number of states that arise, many particle states that arise from that excitation, is exactly the same as the particle hole pairs, and so that's why there is a good correspondence. However, it already starts when you start exciting an electron into an empty orbital, then the unpaired electrons can spin couple in different ways, and there is a larger number of final states that you can reach than would be implied by the particle hole picture. And then, of course, you have the continuum when you start exciting electrons into unbound states, and that is then scattering territory. So the quantum chemistry can be relatively successful here, and the quantum chemistry has very, very little to say about the scattering, and it starts somewhere in the rising edge and then goes to the exahash, and that's why I've marked this here as fifth territory, and I will briefly talk about exahash a little down the road. Yeah? And I will later show you examples or very concrete examples where the many particle spectrum is very, very different from the one particle spectrum. So please keep that in mind. Throughout the talk, I will make a strong difference between the one particle approach and the many particle approach. And I think if one is respectful of that grave difference between the two, confusion cannot arise. Now let's first talk about KH X-ray absorption spectroscopy. As I said, the KH is relatively simple, the transition metal KH. You have a pre-edge feature that arises from the excitation of the 1s electrons into the metal 3D derived orbitals that you see here. These weak features, they're electric dipole forbidden, hence they're weak. Then comes the rising edge where you start hitting the metal N+1 p shell. So in the case of 3D transition metals, a 4p shell. And then, of course, there's the exahash region. And so we're mostly interested when we do the quantum chemistry in the pre-edge region here. Let's briefly talk about the intensity mechanism. The intensity of these transitions is just simply proportional to the golden rule expression, where psi0 is the many particle wave function of the ground state, and psi f is the many particle wave function of the final state, and H1 is the operator that describes the interaction of the electronic system with the light wave. And before I go into that in more detail, this is quite simple and easy to calculate by DFT. So when we do that, so if we have equivalent absorber centers, it's important to localize the 1s orbitals of symmetry equivalent nuclei, like metal nuclei or whatever the absorber is. And then you only include 1s to virtual excitations in solving the TDDFT or Rose's equations. And that is the technical term here is so to say the covalent separation, but it's not a natural covalent separation, it's a covalent separation by assumption. So simply all other interactions are neglected, and that typically is a quite good approximation. And then you calculate the contributions to the transition moments. You will typically use quite large basis sets on the XAS absorber atom in order to treat electronic relaxation, and you will get much better transition energies if you include scalar relativistic effects. So what again is the Hamiltonian H1 that goes into here? And this, of course, light-matter interaction is a relatively complex matter. But if you do a series expansion, you can identify different mechanisms. And the three most important mechanisms here in the framework of X-ray absorption, or actually any other type of optical spectroscopy, is the electric dipole mechanism, where the electric dipole operator is coupling the initial and final states. The next term is the electric quadrupole, and that is already a couple of orders of magnitude smaller due to the square of the fine structure constant here. And then there is a magnetic dipole operator that is even weaker, but has different parity selection rules than the electric dipole operator. And of course, magnetic dipole operator will be important in the framework then of circular dichroism spectroscopy and also X-ray circular dichroism spectroscopy. So these are the principal mechanisms in the light-matter interaction, and by far the most important is the electric dipole. In the upcoming ORCA release, we have included the exact transition moments that do not rely on the series expansion that leads to the electric dipole, quadrupole, magnetic dipole operator. So, but that includes all interactions to all orders. The great thing here is that it's accurate. It's more accurate than using these things in isolation. But the disadvantage is that you lose the mechanism. And I think as most spectroscopists, we hold these mechanisms, the electric dipole mechanism or electric quadrupole mechanism, dear to our hearts. And so there is something to be had by still using that, although numerically we can do better now. And ORCA 5, which is coming in a few weeks, has provision to do so. So here you see a few typical trends in KH X-ray absorption spectra for transition metal complexes. And so you see that, for example, a 5-coordinate transition metal complex is supposed to have a more intense pre-edge than the 6-coordinate species, and the energy of the pre-edge is rising with oxidation states, for example, here from iron 4 to iron 5 to iron 6. It was a beautiful series that we studied a few years ago, and there's about a 1 electron volt increase per oxidation state, which also means that you can use the energy of these features for oxidation state assignments. And by and large, the calculations are really nicely reproducing all of these trends. In almost all cases, most of the intensity comes from the electric dipole. So basically, that is a little bit of p character mixed into the d orbitals through the bonding, and that is what gives the pre-edge its intensity. And only for very symmetric complexes is there a significant quadrupole component that you're sometimes able to pick up. And I know that there are beautiful experiments that have been done on oriented crystals that prove that there is a quadrupole mechanism at work in some cases where the electric dipole is really, really forbidden. But the calculations quite typically predict the intensity trends, the trends in the energies, in the transition energies, and the dipole quadrupole intensity ratios quite reasonably. It can not only be done at the metal K edge, but also at the ligand K edge, and so that is going into the software X-ray regime. And in principle, it's all the same principle. But the nice thing here is that the acceptor orbitals in transition metal complexes bound to sulfur or chlorine, they're not pure metal orbitals, but they carry a bit of ligand character, which is due to the covalent bonding that the chlorine or sulfur or maybe the phosphorus has with the transition metal. And ligand KH spectroscopy is a beautiful way of picking that out by the pre-edge feature. So here's a classic example from Ed Solomon and his co-workers. There is zinc tetrachloride, which has no pre-edge feature at the chlorine KH, whereas in copper tetrachloride there is, and of course that feature here is attributed from the transition of the chlorine 1s into the partially filled D shell of the copper. Copper is D9, so there's just one hole. And so essentially the intensity of that peak is measuring the involvement of the chlorine p orbitals into that copper, into the copper d orbitals. And notice, of course, as I emphasize that orbitals aren't observables, yet I am using the term orbital all the time to interpret these experiments. And I think this is fine. We need this, and we need the orbital picture in order to talk and discuss. Just remember that it's not stopping there. There are far more complicated things happening in X-ray absorption, emission, and all of these experiments that require going beyond the picture of an orbital. Yeah? So these many particle effects are really, truly important, and we will see plenty of that in the talk. There was an interesting analogy, and I think that probably was the first thing I did in theoretical X-ray spectroscopy more than 20 years ago, and that is contrasting the ligand KH intensity mechanism with an optical ligand to metal charge transfer transition. And the big difference is that in the case of a ligand KH transition, the donor molecular orbital is very localized 1s orbital, whereas the acceptor orbital is a delocalized molecular orbital containing the chlorine character. And that's why the intensity of that transition is directly proportional to the amount of chlorine character here, or the ligand character, which is alpha squared. Whereas in the case of a ligand to metal charge transfer transition in the optical region, the donor and acceptor orbitals are both delocalized, and that leads to a factor of R, like the metal ligand distance, in that intensity equation. And of course, that is not there here in the ligand KH. And there has been some confusion about that in the literature that we addressed in that very old paper. And DFT is very successful actually in predicting the trends, both the intensities and the positions of these ligand pre-edge features. And I think maybe about 10, 15 years ago, we studied a lot of that together with Serena and together with Carl Wiechert. And by and large, these calculations are a super helpful guide. That comes up, for example, in these very exciting compounds. These are metal ligand radicals. And it is fantastic how ligand KH spectroscopy can be used in order to pick out the radical character in these various compounds. And so, for example, here was a series with one and the same diethylene ligand and going through different metals and oxidation states. And on the basis of comparing the calculations and the experimental data, it was kind of nice to arrange these compounds into systems that have ligand radicals, whereas those that are innocent. And that's old literature now, but I think it was a lot of excitement back in the day, like how successful these calculations were in aiding the interpretation of the experiment. And so that still stands today. Now let's look a little bit at KH X-ray emission spectroscopy. And so the experiment here is that one S electron is excited into the continuum, and then one looks at all the radiative processes that refill the core hole, and that can be the K alpha radiation, K beta radiation, and eventually the valence to core region. And chemically speaking, the valence to core region is the most interesting. It's also by far the weakest here. Then there is a K beta mainline, whereas the K alpha, I'm not aware that it has great chemical applications because it's not reacting very sensitively to the molecular environment. And now these spectra are, I think I'm sometimes quoted saying that they're criminally easy to calculate just from a totally simple one electron DFT picture, and quite typically the agreement between experiment and theory is quite beautiful, and it lets us really assign the spectra with a good amount of confidence. And so the first paper that we wrote together with Serena was here in 2010. And since then, there has been a flood of really very nice papers. And I think X-ray emission is one of these techniques where Serena students have been most successful in doing the calculations before the experiments, and in the overwhelming majority of cases found that the measurements were just in agreement. What the valence to core region just so beautifully does is to provide an experimental fingerprint of the valence electronic structure. And so in those cases where multiplet effects are very prominent, which is the case for most closed shell molecules, for example, one can make a one-to-one correspondence between the molecular orbital scheme and the valence to core spectra, as Serena, together with her then postdoc Kyle Lancaster and Ken Finkelstein, have demonstrated in this very nice paper, where they have basically shown that the X-ray emission spectrum of ferrocene beautifully maps onto the molecular orbit scheme of the ferrocene, and of course you get experimental calculation again are in beautiful agreement. So it's a really wonderful, beautiful technique, especially X-ray absorption and emission. They're two different sides of the same coin, and they can be used very fruitfully together with very simple and efficient DFT calculations to get a lot of mileage out of it. And with that, I wanted to come to a little bit more difficult territory, and let's first talk about the K-beta mainlines. And what's happening here is, of course, that there is the initial ionization, and then, of course, you create another unpaired electron, and that unpaired electron can couple to the unpaired electrons in the metal D shells. For example, if you have a 3d5 system here, then after the ionization, you have a 6 unpaired electron, and that creates states of quintet and septet multiplicity, one as 1 3d5, and then the K-beta can lead to a whole series of multiplets that are all observable. These are then 3p5, 3d5 configuration, and all of these states must be enumerated and calculated. And here, of course, is already where the one electron picture fails absolutely miserable, so you get zero mileage out of trying to do that with DFT. And in that paper that I'm going to put up in a second, we have analyzed the physical content of that. And let me point out that this splitting here between the K beta 1,3 and the K beta prime, that is mostly due to the exchange interaction between the partially filled P shell and the partially filled D shell, and that will become important. Because you can see that is mostly this exchange integral here, where you have electron 1 and electron 2, and here you have a d orbital and a 3p orbital, and a d orbital and a 3p orbital. Now the 3p orbitals are mostly pure metal p orbitals, but the d orbitals, they're diluted, so to say, with ligand character. And that ligand character then is modulating the size of this exchange integral, and that splitting that you see experimentally, that depends on that exchange integral, and hence, by means of this equation where m and n are integers, depends also then on the metal ligand covalency alpha squared. And Michael Atanasov has worked through the theory of all the n configurations, and you see I have set a scary table pops up here, and here is scary table, and he has worked out for all the n configurations what intermediate and final states can exist for each and every one of these dn configurations, and how in which way they are affected by covalency, because covalency is anisotropic. If you have an octahedral complex, you will all know that there are metal T2G and metal EG orbitals, and they're interacting different with the ligands. The EG orbitals being sigma anti-bonding typically are more strongly diluted than the T2G orbitals, which are involved in pi interactions. And based on the table, you can then draw yourself a graph that shows you how that mainline splitting here, that is splitting, and it's normalized by 4G1 plus 42G3, which are the Slater quantum parameters, but they're essentially reflecting that exchange integral. And so you see the more unpaired electrons you have in the ground state, obviously the larger the splitting of the mainline will be, because there will just be more exchange interactions with the 3p5 shell. This is the curve drawn for high spin states, and here in blue are the respective low spin states. And of course, it's also depending on the oxidation states. And in the paper, we've also investigated how that splitting reacts to the oxidation states. But basically, this figure suggests here that you can use mainline splitting in order to assign oxidation states. And by and large, it's true, but there is an important component to it that there is an aspect to it that needs to be taken into account. And the oxidation state dependence, of course, comes from the fact that, like, the more oxidized the metal is, the tighter its radial function will get, and the tighter the radial function gets, the more exchange interaction will be between the p and the d shell, and that, of course, will increase the splitting. Now, of course, if you go to a given oxidation state, and here we have the examples of 3D5 systems, and we have worked through the high-spin hexahalide complexes, then, of course, the splitting is just modulated by covalency in exactly the way that I've shown you before on that other slide. And you can actually make a very nice correlation between the covalent dilution of the metal d orbitals and the experimental mainline splitting. So that's pretty much a straight line, at least for theoretician, it's a good enough straight line, with a very good correlation. And essentially what you see here then is that there is a correlation between these orbital reduction factors T and E in Atanaptov's table and the actual splitting of the mainline. And you can calculate these spectra quite nicely with the RACI approach. So that is the experiment for these hexahalides. That is the RACI calculation, and the experimental trends are very well reproduced, even pretty much quantitatively reproduced. It's actually easy to do. That is the input for ORCA for doing these calculations, and I'm sure that Dimitris and Anneke will walk you through how to do that. It's a few lines of input. You just need to count your electrons right, and that's all that is required, and the calculations just take a few minutes. Now I want to come back to that one qualification that I want to make in terms of relating the mainline splitting to oxidation state, and that is, yes, it is reacting to oxidation state in exactly the way that this graph is showing. However, the splitting is also modulated to a significant extent by covalency, and so the covalent reduction, so basically dilution of the metal d orbital, will also reduce that splitting by means of that equation that I've shown you. And hence, if there is a nicely covalent bond, you can have a D5 system that in terms of splitting looks like a D3 system, right? So that would be a D3 system, D4 system, D5 system. And so that splitting here that you have for the most covalent system, that would be the hexabromide, that is rather similar to what you would observe for a model D3 system here. So the mainline splitting is indicative of metal oxidation state, but it's reduced through covalency, and one has to be careful when one makes these oxidation state assignments. That is the message here. Let me come to another subject that we have studied a while ago, and that we really poured our hearts into to a very large extent, and that is XFs and quantum chemistry. I don't have much to say about XFs, but I just want to say one or two things about XFs when you combine it with quantum chemistry. And of course, the most prominent part here is the oxygen evolving complex. And as you know, there's a very rich history of discussing structural models for the oxygen evolving complex that by now have been pretty much settled. But there was a certain amount of reasoning that was involved with the XFs of the oxygen evolving complex. And for a while, people wanted to use the following argument. So they have calculated the structure, say, by some theoretical method, be it QMMM or be it something else. And they have the observed XFs that, due to the wonderful work of Johannes Messinger and Giuliano and many others of their collaborators, are available for all of the intermediate states of the OVC. But then basically the argument that people wanted to make is that, like, say, look, I have calculated the structure and then I run it through FEF and get a predicted XF spectrum, and that matches experiment, hence my structure must be right. And there are two caveats with that. And the first is simple, and that is the second here, that said this statement is just too strong. You can never say, because your calculated spectrum agrees, that is the right structure. You can only say that the structure is consistent with the observation. However, the argument, and that is the point that I want to make here, is only solid if you prove that the algorithm that generates the simulated spectrum, not the fit, right, is reliable. Hence, I have to demand that the algorithm, if I know the structure and I know the XFs, that algorithm must give me the right answer, right? Because otherwise I cannot rely on anything that the algorithm predicts when I don't know the answer. And please let me point out again, we're talking about now predicting, so not fitting the XFs. Yeah? So that means there is no input from the experiment. You take the structure and predict the XFs. Yeah? Now, then the unanswered question at the time was, how reliable are these XF calculations? And we have teamed up with John Rear here, and it was a very interesting study. We had wonderful discussions that I enjoyed very much. So let's first look at what the XFs really is. We all know XFs arises from scattering of the electron after you excite it to the continuum, and then the electrons are scattered on the neighboring atoms, and there is constructive and destructive interference, and that, of course, holds the structural information. And by doing a Fourier transform, you can go into position space and then fit either the position space or the momentum space spectrum, and you get your answer. Now, of course, this is the XF's master equation, very well known, and it consists of a sum over pathways, scattering pathways, and NP is the length of that pathway, RP is metal ligand distance, and sigma is the Debye-Waller factor. Yeah. So basically, these are the things that you need in order to predict the XF spectrum. Yeah. And so there's a number of things like FF that comes from tables that physicists have compiled that are stored inside FEF. There's scattering amplitudes and phase shifts and mean-free photoelectron paths, and all of these things you know better than me. But the three types of quantities that are relevant in this context are RP, the length of the pathway, NP, the number of equivalent scattering pathways, and so basically that is just geometric information that comes from DFT. And then you have to have the Debye-Waller factor. And you can, in principle, calculate these Debye-Waller factors from density functional theory, or in principle also other theories, but DFT is the most practical. And now, how you do that? The way we have written it down in that paper here that is authored by many, many authors, but I want you to pay attention to the fact that John Rear is an author on that paper, and we have discussed it extensively. So the bipolar factor in principle is related to the vibrational density of states, and the vibrational density of states can be calculated from DFT frequency calculations. And so you can evaluate these equations theoretically, and then you have eliminated that as a fit parameter or fudge factor, right? And so that means you know everything, right? So you have the length of the pathway, that is all DFT. Oh, I apologize. I'm being the victim of my animation here. So you know the length of the pathway and the number of equivalent scatterings from the DFT geometry optimization, and calculate the bipolar factors from the DFT frequencies. And that means you can evaluate the XR spectrum completely theoretically. And then we have tested how well does it work when you know the answer. And so we had a number of manganese complexes, both monomers and dimers, where we knew the structure from high-resolution X-ray crystallography, and we knew the XRs, and we also had fitted XRs. And so for the simple monomers, it works quite well. And so you see here in black is the experiment, and red is the fit. And then in blue and green are two different calculations of the XR spectrum, purely from DFT. I would say that's not really bad. And in the paper, we go into detail comparing them. So if you take a closer look, then the distances are predicted well. The bipolar factors aren't predicted particularly right, so they vary by factor of 2 to 3 from the fitted values. But by and large, that is not a train wreck. But then what happens for the manganese dimers? And for the manganese dimers, so you see that the calculated XR spectrum has absolutely nothing to do with the experiment. So these are all calculations here, and they don't agree with the black line at all. It's an absolute fiasco, and it is really here where the bipolar factors are really hitting you. They can be off by an order of magnitude, and then the calculated excess just goes to pieces. And it's particularly these metal scattering pathways. They're extremely bad. So basically, what that means is I'm saying that PHEF is a really wonderful, powerful, great tool. It does an amazing job of simulating and fitting XR spectra. We all know these fits are complicated and often underdetermined. The most complicated of these parameters are the bipolar factors. Just taking a global value is not cutting it. And the bipolar from the DFT can be helpful, but they are not accurate. And at least our conclusion at the time was that XR spectra cannot, or at least not yet, be predicted accurately and confidently from quantum chemistry. And that also means that the argument cannot be made that if you have XR spectrum that you just theoretically generate from a DFT geometry optimized structure agrees with the experiment does not carry much weight, because you know that you get the wrong answer when you know both the spectrum and the structure. And so I advise some caution here. I hope that in the future quantum chemistry will be a better partner of the XR experimental community, but at this point in time, I think we have to admit that we're not there yet, and we're not in a place where we like to be. Now, let's go to more complicated spectra, and I want to bring up here the LH. And the LH absorption spectrum arises from exciting 2p electrons into the 3D manifold, and of course that is a Laporte allowed, so dipole allowed excitation, and that means the LHs are much lower in energy, and they're also much more intense than KHs. Because we're looking at dipole allowed transition. But there is a more important aspect of it, and that is a very strong spin orbit coupling in the 2p shell, in the partially filled 2p shell, that is splitting the LH apart into an L3 and an L2H in a way that you are certainly all familiar with. And now here is one of these cases where I want to make a strong point between multiplets, states, and orbitals. Now let's look at a specific example of the high-spin D5 configuration. And here we have then the 2p shell or the 3p shell. For that argument it doesn't matter. And then we do that excitation into 2p5 3d6. And like how many states arise from that? If you count it out, there are 1,512 many particle states that arise from that excitation, right? But you only have 3 times 5, meaning 15 particle Hall pairs. Yeah? That means that as a matter of fact, the many particle Hamiltonian has 1,512 eigenvalues, and that means there are 1,512 possible transitions, and these 1,512 possible transitions, they all contribute to the observed spectrum. And it is not conceivable that with 15 particle Hall pairs, you can calculate a spectrum that means there are 15 peaks if you do a particle Hall calculation like you do in TDDFT or other methods that are being used that live in the particle Hall manifold. So you're missing the order or like the number of final states by 2 full orders of magnitude. Yeah? And so if you actually do the calculation and diagonalize the many particle Hamiltonian, that is then your eigenvalue spectrum. That is what's observed in the experiment, and that is a particle Hall spectrum from TDDFT. And you see that this one and this one, they have nothing in common. Then it's absolutely impossible to calculate a realistic LH spectrum of an open shell transition metal using TDDFT. Now, of course, the D5 configuration is the most extreme, but it holds for any open shell configuration in the electronic ground state. In principle, it could be okay for D0 systems. Experience shows it's still not great there, but at least in D0 systems, it's correct with DFT, qualitatively correct, quantitatively, it's not so great. So here you really have to do something. And what we had to do, or what we wanted to do, is to come up with a wave function method. And it's because the multiplet problem in DFT is not solved in a satisfactory way. And that means what we have to do, and I will just lift the curtain a little bit about how these electronic structure methods work. So we have to generate these many particle wave functions, and we have to spin adapt them. So both the total spin S and the magnetic spin quantum number M sub S, the magnetic sublevels of a given state, they need to be explicitly represented. Then we also need to take care of the fact that the spin orbit coupling operator is a 2-electron operator. It contains 1 electron part, and then it contains the spin same orbit and spin other orbit contributions, and you need to take care of them. And so that's a fairly complicated electronic structure problem, but it's doable. What helps a lot is in calculating the spin-orbit interaction is the Wigner-Eckert theory that lets us reduce a whole block of these coupling matrix elements between states of the same, or of one configuration I and J with spin quantum numbers Sm and S prime N prime. So that's a 2s plus 1 times 2s prime plus 1 matrix, and they can all generate it by calculating one matrix element, that is the reduced matrix element, and then the Clebsch-Gordon coefficient. These are technical details that I don't want to dwell on, but you get a general idea of what it is. Yeah. So basically, in the development of process, what we wanted is to make sure that the ground state reference function is a spin eigenfunction. So we use a restricted open shell reference function that only pertains to a certain class of ground states. So, for example, an antiferromagnetic solid at this point in time we couldn't do. Dingtris might tell you that meanwhile we have exciting new results that also lets us treat antiferromagnetic systems, but at that point we couldn't do it. So as long as you have a restricted open shell reference function, you can only derive with it. So you keep the spin symmetry in all excited states. You get the multiplets correctly by letting them interact with spin orbit coupling through quasi-degenerate perturbation theory. And in order to be applicable to large molecules, we also restrict the excitation space to single excitations at the configuration level, not at the determinant level. Yeah? And we have developed that into a tool for spectroscopy that can do a lot. Here's one thing that I wanted to just at least mention in passing. So if you have a given number of unpaired electrons, you can typically generate more than one spin eigenfunction from it. For example, you have 4 unpaired electrons. There's only one way you can couple 4 unpaired electrons to a total spin of 2. But by the logic of so-called branching diagrams, there are 3 ways you can couple 4 unpaired electrons to a total spin of 1. And you explicitly need to take care of all of them because they are linear independent and they all show up then in the final nanoparticle spectrum. That means they also show up in the experiment. And this gets all super technical, and in the interest of time, I'm just skipping over these few slides in order to not complicate it too much. So you see, there is quite complicated equations that were coded at the time by Michael Rümmelt as part of his PhD. And he did a fabulous job on it, and then Dimitris is really the person who developed the program into the powerful tool it is today. Yeah. You can calculate somewhat large-ish molecules. As I said in the introduction, it was 100, 150 atoms maybe. By now we have so-called PNO-ROSES method that can go further, and that basically gives the same results. But the nice thing is now you can actually calculate transition metal LHZ. Is here the example of ferric tetrachloride, and the agreement between theory and experiment is pretty good, so you get all of the principal features, but a few features actually are here in the experiment that are missing. Now these calculations are suffering massively from the fact that Hartree-Fock is such a terrible method to treat transition metal complexes. And they also suffer from the fact that we neglect dynamic electron correlation, and so what physicists would refer to as screening. And that is very valid criticism, and it does limit the usefulness of the method itself. That's why we came up with the so-called DFT ROSES that is introducing very few global in terms of the periodic system, empirical parameters that we use to scale these matrix elements here, and that basically is aping or in a very average way taking care of the dynamic correlation. It's not a perfectly accurate or perfectly satisfactory solution, but at the time, and this was basically 10 years ago, we needed something that was a practical tool, and it absolutely is a practical tool. It's also nicely used by the community now, and I'm very, very grateful and glad that it is. I hope that in the foreseeable future we come up with something more rigorous, but for the time being, the slightly parameterized method, the DFT ROSES, is a very nice method that works very well. So basically, you see we have 3 empirical parameters that were fitted to a set of reference data and that define the DFT ROSES method. And the ROSES method itself is a pure ab initio method with the limitations that I've just mentioned. But of course, the DFT ROSES then is a more successful method, and there are still these features are missing here, but by and large, there is quite a lot of improvement in the qualitative shapes of these spectra. Meanwhile, Dimitris has done a really pioneering study, and that was to apply multi-reference coupled cluster theory to these very same spectra of iron, ferrous, and ferric tetrachloride, and the agreement here is really beautiful. And these are calculations that I do not recommend doing to anyone who isn't an expert. They are complicated, they are super expensive, and I don't think we could do anything that's much larger than these molecules that we have studied here. But they are available, and they show actually that the agreement with the experiment does improve. It gets very, very accurate here. And so for this kind of reference type quality calculation, there is a possibility to do that. At the moment, still at crazy computational cost, but I sincerely hope that it will be possible to simplify that in a way that makes this applicable to larger molecules, and then it will get much better. Dimitris has done a lot of work in using embedding methods to treat solids and surfaces. I will only scratch the surface here, but it's typically quite successful. And so here you see a number of iron complex LH spectra. Works really, really well. And you will hear much more about it during the workshop. Now I want to treat two more subjects that are even more advanced, and the first one is XMCD. And I wanted to add a short note on XMCD. So MCD in the X-ray regime works pretty much exactly like in the visible regime, which is how I was brought up in MCD spectroscopy in the UV and visible region. But the principles are the same, with the one exception that somehow the XMCD and community uses the exact opposite convention from the visible MCD community. So in our world, we take the difference between LCP and RCP photons, and it's my understanding that in XMCD the opposite convention is followed, which means we need to like multiply ourselves by -1 when we want to talk to each other about it. But the principle is the same. So we have a light source producing through a modulator, RCP and LCP, right and left circular polarized light that is being transmitted through the sample that is sitting in longitudinal external magnetic field that can be varied and then picked up by the detector, and taking the difference defines the MCD signal. If you subtract out the natural CD at field 0, then that is what the MCD is. And the MCD in principle, of course, like the very most direct way you can express the MCD intensity is saying that is a probability to absorb a left circularly polarized photon, that is a probability to absorb the right circularly polarized photon. You subtract them from each other, and you sum over the initial states weighted by their Boltzmann population, which of course is dependent on magnetic field and temperature, and the final state that you can reach it. They have no initial population. That's why this is the master equation for MCD, and that can be further developed. MCD, of course, has several dimensions. It has a spectral dimension when, like, on an energy axis, and it has a magnetic dimension that can be explored by varying the magnetic field and the temperature. I don't want to go into that, but I think XMCD is really no different from regular MCD in that respect. Now, many years ago, I have developed this effective theory for it, where you can express the MCD intensity as from just the magnetic properties of the ground state multiplied by taking spin expectation values and multiplying them with effective transition moment products. And so that gives us the opportunity to do the MCD calculation in just a similar way as a spin Hamiltonian calculation. But that is not really the point here. Now we want to talk about XMCD, and oh, sorry, I forgot to mention that. In order to get MCD intensity, you need spin orbit coupling. And there are three principal mechanisms here. The first one is a direct spin orbit coupling between the ground state and the final state that you reach in the excitation. That is a very small and also weak mechanism. So the main mechanisms here is that the ground state spin orbit couples with an intermediate excited state, and J is the final state that you reach. That often gives MCD of just one side. There's the other coupling mechanism where the intermediate state spin orbit couples to the final state that always gives a pair of excited states that have MCD of opposite side. That's relatively easy to prove. And so these are the main mechanisms in terms of spin orbit coupling that are operative. And in principle, you can approach, of course, the MCD in a very brute force way by setting up a master matrix that contains many particle wave functions I and J that you generate from any of these methods that I've mentioned, be it like RACI or ROSIS or CASIS CFNF-PV2 or MRCI. any of these methods can generate these many particle wave functions, and then you let them interact through the Born-Oppenheimer-Hamiltonian spin-orbit coupling and the Zeeman operator, and you diagonalize that matrix, and then you have a magnetic field dependent relativistic many particle eigenstates that you can then use to evaluate the intensities, and then you have to average it obviously over field orientations, and then you can generate the NCD spectrum in absolute brute force. And we have studied here a number of vanadium ACAC complexes. That is an oxo-vanadium ACAC2, and that is it's a vanadium 4 complex, and that is vanadium 3 complex is ACAC3. And so we can calculate both the XAS and the XMCD from, in this case, it was NFPD2 calculations, and you hopefully agree with me that the agreement between theory and experiment is quite nice. And so that already proves that there is a nice and accurate, usable theoretical tool there in order to calculate XMCD spectra. And in the process of the paper, we have revisited something that I understand is very prominent in that field in XMCD, and that is the validity of the sum rules, where from the experimental spectra, with under a number of assumptions, expectation values for the spin and orbital magnetic moments can be derived. And we have done that, and we have derived the same expectation values from our many particle wave functions that are in good agreement with the experiment. So we think that our calculated spin and orbital moments are accurate too. And as you see, that sum rule is not very good, as even like gives the wrong sign of the orbital moment in the case of Leo ACAC2. And it's basically rather inaccurate. So we have concluded in the paper that if you compare the magnetic moments determined from XAS and XMCD with squid, like, there are deviations by more than a factor of 7 in the case of the opto-ACAC and more than a factor of 2 in the ACAC3 complex, and that means that the sum rules just break down. And they shouldn't be used to describe the magnetic properties of the study of vanadium complexes. And in our experience, that is actually more general conclusions. So what we believe that the sum rules are not valid. They are derived under assumptions that typically are not met in 3D transition metals. They get much better as you go down in the periodic table. So for heavier metals and rare earth systems, they become much better, but for much of the 3D series, at least, we call the validity into question, and in our opinion, the sum rules shouldn't be used in that context. And it's a complicated, lengthy, and detailed argument that, if you're interested, you can read about it in that recent paper from last year. Last subject for today, before I will lead you to the rest of the workshop, is to take a brief look at RIXS. And so that is a second order process. So it's not described by a single photon process, but by a double photon process. And that is then based on the Kramers-Heisenberg-Dirac equation. The idea here is that you go from the ground state to an intermediate excited state, and then you emit into a final state F. And so that these intermediate and final states can be anything. And so that is a super versatile but also complicated technique that you have there. And basically one can take, just as in the case of XMCD, one can take this very fundamental equation here and just plug the many particle wave functions in and come to a numerical truth. But we wanted a little more than that. So we have worked in that paper that I hopefully have cited here. Yeah, in that paper, we've worked out quite a number of relationships. So if you take the Kramers-Heisenberg formula and you focus on one intermediate state that is actually in resonance with the photon energy here, then of course that one intermediate state will dominate the intensity mechanisms, and that means you can take that equation here for the polarizability and simplify it in this way, where you simply sum over where the sum goes over final states, and then you have the coupling of the final state to the intermediate state via the electric dipole operator, and the intermediate state to the initial state via the electric dipole operator. And we call that the direct term. And if you sum the direct term over all intermediate states, that would give you then a fair representation of the spectrum. But of course, there is that square outside the summation here, and that means if you evaluate it rigorously, there are also terms that come from pairs of intermediate states, and these are called interference terms. So basically, we have made the distinction between those direct terms here that I've defined here, the total RIXS that you obtain by rigorously evaluating this equation, and then the interference terms, which is different of the total and the direct term. And then, of course, you can also simplify that to the XAS and XES spectrum, and we have done that in our implementation. And so basically all of these quantities, the XAS, the XES, the interference terms, the direct terms, and the total RIXS are available. And the system we have looked at are these very interesting tetracyanonitridomanganese systems that Serena has studied together with her group for a while. And they have a nice RIXS spectra, but what caught our eye really is the resonant emission. So basically here you have the emission axis, and then you see whether you excite into the pre-edge or the rising edge gives you a drastically enhanced resonant emission in the pre-edge feature. Likewise, here is the pre-edge absorption, that is the absorption axis of the RIXS. And so depending on whether you look at the K-beta 25 or the K-beta mainline, you get very, very different pre-edge intensities. And we wanted to understand that. And so most of that paper that I'm quoting here is devoted to understanding these resonant absorption and emission processes. So first of all, we have to assign that it's a relatively simple electronic structure, and so the absorption, X-ray absorption pre-edge is here from arises from excitations of the 1s electrons into the metal 3D derived orbitals, and there is Z and XY allowed transitions here by going into the X squared minus Y squared or the DZ squared orbital. And then, of course, there are the rising edge transitions. Likewise, these Rose's calculations are in actually fairly good agreement with experiment. They nicely reproduce here that pre-edge feature. Then, of course, how accurately that part of the spectrum here in the rising edges reproduces open to debate, of course, because the experimental resolution is not great. But by and large, both the XES and the AS are nicely reproduced, and so I'll show you the calculated RIXS in a moment. And you can basically, on that basis, assign these peaks. The most important one is that the first transition here, that is arising from the very strong interaction of the metal DZ squared orbital with the nitrogen of the nitridonitrogen PZ orbital, and of course that gives rise to a nicely Z-polarized transition that is directed along the metal nitrogen bond. Now, what we learned in that study in a nutshell is the following: that is, in order to get resonance enhancement, you need transition moments that are not orthogonal. So that means that the transition from the ground state to the intermediate state must have a transition dipole moment vector that is not orthogonal to the transition dipole moment vector that you get from coupling the intermediate state with the final state. So in other words, you will get, if you excite into the pre-edge where you have Z-polarized transitions, you will only resonantly enhance emission features that are also Z-polarized, whereas the XY polarized transitions, they will not be enhanced. And that is the principal feature. And that is worked out in great detail in the paper. And then, of course, you can also like modulate that through interference terms. And so you can actually compare the Z-polarized pathway, which is in blue here, to the calculated spectrum, resonant X-ray emission spectrum, to the total spectrum, and then the interference terms. And that, of course, depends then on the on the emission energy. You see that here is the XY polarized pathway, and there the interference terms are big. Again, this is all a complicated paper and a complicated analysis. I only wanted to scratch the surface here and saying that you can use these calculations now. ROSES and all of the other tools are available in order to calculate that. And you can also use that to get insight into the origin of these features. So in summary, most of the phenomena observed in X-ray spectroscopy can be calculated using modern quantum chemistry. TD-DFT or DFT is mostly useful and efficient for KH spectroscopy, and for more complicated spectra, wave function-based ab initio methods are mandatory, not only recommended, I think they're mandatory. And various of these ab initio methods are available in ORCA, including ROSES, NeFBD2, and RACI. And I hope that you will have a lot of fun practicing with these methods and everything I've told you about in the rest of the workshop. Enjoy.